In this first problem, we're looking at a simply supported beam, and we are going to try and determine the expression for the distributed load as a function of x. So we're looking for W of x. That is the part A of this problem, and part B is we need to determine our support reactions for this beam. So if we look at this loading, this distributed loading, we see that it goes from 200 Newton meters up to 400 Newton meters. And that characteristic of this curve is a linear line or a straight line. Of course, then we know from that, just by observation, that this is a formula that we typically would have for a straight line is y equals mx plus b, or W of x, our distributed load, plus b. M is our slope, and b is our y-intercept. To solve for the slope, we would have m equals our 400 newtons per meter. It's our change in slope. This is our rise. Our rise is 200 Newton meters divided by the run, or the length that we're looking at, 6 meters. So our slope is 33.3 newtons per meter squared. The next step is to solve for our y-intercept. So right now we have W of x is equal to 33.3 newtons per meter squared times x plus b. We know at x equal to 0, W of x, right, equals 200 Newton meters. Therefore, B equals 200 Newton meters. So our equation is W of x is equal to our 33.3 newtons per meter squared times x. X is going along the length of the beam, plus b, and b is 200 newtons per meter. Again, this is our x axis, this is our y-axis. Okay, so the second part is to determine our support reactions. So we're trying to find AX and BY. Okay, and we can't do it for this distributed load, so what we want to do is be able to find a force, wherever that force is, F, solve for that force, and then we need to know the location of that force. We need to know this x bar location for it, right? And we know this formula that we've used already. Finding x bar is equal to our integral of x times the distributed load dx divided by the integral of the distributed load dx, and that in the denominator is our overall force F. So let's look at the denominator first. Again, this is really equal to F dx. We have our equation for our distributed load that we can put in here. There's our equation. If we integrate this, we get that F is now equal to 16.67 newtons per meter squared times x squared plus 200 newtons per meter x. And we're going to evaluate that from 0 to 6 because we're starting out from 0 and going out to 6 for this. And we see if we integrate this and put in our values from 0 to 6, we end up with 1,800 newtons. I want to kind of take a quick look at our units to make sure that seems to make sense. We know this x squared is in meters, and that'll be meters squared, so that will cancel out with our denominator. We end up with just newtons. Here we just have meters. That cancels out, and we end up with just newtons. So carry your units along to make sure that things look right. So now if we look at our diagram, we now know what F equals, right? This is equal to this 1,800 newtons. Last, we need to find this x bar. So go back to our equation. And we're going to find this equation here and write that out. So we will have the integral of x times w dx is equal to 0 to 6 of 33.3x squared plus 200x. I've already distributed that x in dx, and if we do a quick integration of this, that ends up being 1.11x cubed plus 100x squared, evaluated between 0 and 6. This ends up being 6,000 Newton meters. Okay, so now we need to just put it all together to solve for our x bar. X bar, again, is equal to our values that we just found, the 6,000 Newton meters divided by 1,800 newtons. And that will equal x bar, which is equal to 3.33 meters. Okay, so now we have all the information we need. We know the weight or the force is 1,800 newtons, and the location of x bar is at 33.3 meters. Let's evaluate this free body diagram and draw in what we have right now and what we know. Okay, so I've drawn in the forces that we have on here, our reaction forces. Of course, there's a pin and a roller. It's a simply supported beam. Here is our x-axis. Please ignore the distributed load. We're just going to look at these red forces. Right? We've replaced that distributed load with that 1,800 newtons. So now we should easily be able to find a y, by, and a x. If we do a quick summation of forces in the x direction equals 0, we see that that is equal to ax, or ax equals 0. That's typically what happens in these simple supported beams. The next step is to solve for either ay or by. The best way to do that is to take moments, either a or b. I typically like to take it where my pin is. It's not necessary that it's there. It could be at either end, but that is what I'm going to do. So those summation of the moments must equal 0. I have my 1,800 newtons that I just calculated times its moment arm. This is the moment arm that we just calculated of 3.33 meters. It is a negative moment that we have. It's going in a clockwise direction. And then we have our by. By times the moment arm of 6 meters. That will give us a value for by, which will be 1,000 newtons. Last then, we're all familiar with this, just summing forces in the y direction, and we get a y minus 1,800 newtons, and then plus our by, which is 1,000 newtons. We see that ay equals 800 newtons. And now we have solved this problem with a distributed load, and we have also found the equation for w of x as a function of x, the distributed load as a function of x.